All right, so last video in chapter 11 series here is the titration of a diprotic weak base with a strong acid. So we're sort of bringing a couple concepts together here. We're bringing that polyprotic concept, so thinking about what is the dominant species at each given pH, and we're doing it from the base perspective. So bringing a couple different things in here together. Disclaimer for this video, and the reason why I don't have the video on is I actually just had eye surgery last night. My eye is in quite a lot of pain and it's taped shut, so you probably don't want to see that. Um, at the same time, my depth perception is off, so my handwriting might be a little less legible, though I think it should still be functional. But it may take me a little bit more time to get things written, so this video might be a little bit distended compared with normal. So the system we're working with here is this diprotic system. I'm giving you the titration curve to start with, but often, in a real problem, this is what we would be computing. But I like to have it here so that we can think about each step and then correlate it with what reality is here. There's actually two curves here, two titration curves labeled A and B, A being the blue one, B being a black one. So A is what we're going to work through each of the points there, A through E, and that has a 10 milliliter dibasic solution, just a generic base with a pKb1 of 4 and a pKb2 of 9. And we're going to use a 0.1 molar HCl titrant, and then I just wrote out the two protonation steps here. So we have base, and that protonation step, first protonation step is dictated by Kb1, and then the second protonation step is dictated by Kb2. And if we look at our titration curve, one thing that we have to be really careful about here, and I mentioned this in earlier videos when we were talking about bases in Kb, is that pH, in pH we're talking about Kas, and so that's why you don't see for this first Kb, the Kb is at 4, but see our actual point here, B, where pH is equal to pK, that's pH is equal to pKa, remember, so that's why it doesn't correlate there. So we'll have to convert that Kb to Ka or vice versa for these things to match up. So just giving you that little disclaimer there so that if it doesn't make sense, it's because we're working in Kb space versus Ka space, or pH space versus pOH space. So first thing I always like to do in any titration is to compute the volume at equivalence. As I mentioned several times before, that gives me perspective as to where I am in the titration. Am I pre-equivalence, at equivalence, post-equivalence? And in this case with the diprotic system, I have two equivalence points, which means I have two volumes at equivalence. So having both of those values gives me a pretty good sense for how I should be thinking and how I should be computing those concentrations, and it also gives me a really quick idea of what's going to be predominant in the system at that volume. So we're going to compute volume. I'll just write VE1. That's the first equivalence volume, which in this case is going to be coincident with C. That's where our first equivalence point is. And then our second equivalence volume is going to be coincident with E. We'll walk through in subsequent steps in this video how to compute the pH at each of those steps at each equivalence point. But for volumes, it's simply M1 V1 twice. So we would have the concentration of our original dibasic solution. Let's see here. I forgot to write that up. That's our solution here, and I'll just write our base formal concentration, or B naught, is equal to 0.1000 molar. So that's what we're starting with. So we just need to start with our base concentration, so 0.1 molar times its volume equal to the concentration of our titrant, which in this case is also 0.100 molar, multiplied by our first equivalence. So this is pretty easy to compute. So VE1 has got to be 10 milliliters. And remember, that's to drive this first step. step 1 to completion. And if we had a certain concentration of B, which was 0.1 molar, then if we had our titrant at 0.1 molar, then of course it's going to take exactly 10 mils to do that. Now we've converted everything, though, at that point, after we've added 10 mils of acid to the solution, we've converted all the original B now to BH+. And so it should be intuitive then that VE2 is simply going to be 2 times whatever VE1 was. It's always going to be double, and that's going to be the case always because you're talking about the same species, you've just protonated it. So whatever our formal concentration was of B, that is the formal concentration of the next protonated species, again, because you just converted it. And so in this case, that's going to be 20 mils to get to our second equivalence point, which makes sense according to our titration curve here. So I just grabbed those values and shrunk them down so we have space, but we can be reminded of them, and they're in the top right in red right now. All right, so we're going to start with point A on the curve, and this is really similar or exactly the same as our initial point on the previous titration curve we computed, except now we're dealing with the weak base in water instead of the weak acid in water. But at this point we haven't added any titrant, and so to compute this, it's just adding a weak base to solution. In this case it's a weak diprotic base, but we're going to make some assumptions. As I mentioned before, when you have a diprotic system, we're going to make assumptions that as long as the pKs of the two protonation steps are far apart, usually like around 1,000-fold apart or 3 orders of magnitude apart, then that's a reasonable approximation just to assume that it's monobasic or monoprotic. In this case, our pKb1 is at 4, pKb2 is at 9, that's 5 orders of magnitude, which is 100,000 times different. So this is going to be a reasonable approximation, meaning that the differences here, the error here in this assumption, isn't going to manifest until the fifth significant digit, so we won't see it. So we just need to pretend that we're adding a monoprotic base. Even though it's diprotic, we're adding a monoprotic base to water, which we can write out that equation or reaction, which protonates and gives us hydroxide. And then our steps here are that we had some formal concentration of B minus X, depending on how much of it dissociates here. And then we have some amount of BH plus X, some amount of hydroxide X here that dissociates. This protonation step, because it's the first protonation step of B, becomes dictated by Kb1, so we can write an expression here which is going to be Kb1 equal to x squared over F minus X. So this is sort of our classical form for any type of change to equilibrium. So remember, at this point you can solve this 2 different ways. One, explicitly using the quadratic, so here's the quadratic form of the expression, or you can simplify by assuming that this x here is negligible. You got to be a little bit careful here because Kb it would manifest in the 4th significant digit here. So it's up to you how accurate you need this to be, but you would need to know how to do it both ways. It's important to understand when to use the approximation, which we've sort of belabored the point in many videos. So if I solve this explicitly with the quadratic, what I get is a value of 3.11 times 10 to the minus 3. Remember, this is always the point of you know, especially if you're sort of being hasty, you sort of think that this is the proton concentration, but when we're talking about bases, X is hydroxide, so this is equal to hydroxide ion concentration. So we need to convert this by using Kw over hydroxide concentration equals proton concentration, and then take the negative log of this to get our pH, which in this case the pH is 11.49. Dead giveaway if you accidentally take the negative log of the original value is you're going to get a really small pH, which doesn't make sense if all you've added is a base to water. And so it's helpful as you're doing these computations to have sort of a hand-drawn titration curve. This is what I always do, where I have pH versus milliliters of, in this case, acid being added, and I put my points up on that curve as I'm computing them. And so this would be at 0 volume being added. If you computed that and it was down here in the pH 2 or 3 range, then you would say, it doesn't make any sense at all. And then you can sort of reverse track or reverse course to figure out where you made a mistake. So in a question that you may be assessed on this knowledge, I'll probably end up having you draw the curve anyway. And so often you'll just be computing each step and then drawing those points up. And so if one point all of a sudden doesn't fit the natural curve, then that's a giveaway that you should reassess. Okay, so just a reminder, how did we get here? We didn't add any acid yet, so we just assumed base was being added, but the key approximation here was that we're assuming this to be a monoprotic system or a monobasic system. So it only accepts one proton. We're not concerned about the second protonation step because that second protonation step has an equilibrium constant that's 5 orders of magnitude smaller than the first step. And so we deemed that a reasonable approximation. Second point we'll compute here is point B. So hopefully you're looking at point B and saying, yeah, I know how to do that point. That makes sense because that's dead center of the first buffer region. So what does it mean to be in the first buffer region? What does it mean for what species are present? Well, that means you have, at least in the first buffer region, you have a mixture of the fully deprotonated base, B here, and BH+. And if you're exactly halfway between in that plateau region, then that's a specific region where the concentration of the original base is equal to the first protonated form of that base. So I'm giving this example is walking you through how to compute that, and that's an easy one. But the same process here and using the Henderson-Hasselbalch would be true anywhere between points A and C. So the same process is going to be used here, which just means that you need to use the first Henderson-Hasselbalch equation to compute this. So Henderson-Hasselbalch is pH equal pKa plus log base over acid. In this case, the acid is the protonated version of the original base. But be careful here because we are using the acid form of the Henderson-Hasselbalch equation. So I showed you what the base form of this was in I think chapter 10. You can use that, or you can use the acid. You just need to be really careful what pKa or pKb is associated with it. How do we know which pKa or pKb is associated with this? Well, first, we know just intuitively that the two species in solution at this point, we'd already made that assertion, is going to be the original base and the first protonated base. And so that means that we're dealing with KB1, but we're using a Henderson-Hasselbalch expression that's dealing with pH, which needs pKa. So what pKa is associated with pKb1? Well, if you look at this, it may not be totally intuitive, but if you think about it from the final form of BH2, 2+, that's the fully protonated acid form. If you allow that to go backwards and deprotonate itself, then its first deprotonation step will be Ka1, which would be associated with Kb2. And its second deprotonation step, when it's in the form of BH+, would be its Ka2, its second dissociation. So in this case, the pH here is going to be equal to pKa2 plus log B over BH+. If that doesn't make sense, pause it, rewind it, watch it a few times. Hopefully that makes sense because it's all with respect to either the base or the acid. So we call it Kb1 because that's the first protonation step. Kb2, it's the second protonation step, but we call it Ka1 because that's the first dissociation step of BH2, and Ka2 is the second dissociation step. So we need to compute what pKa2 is. So remember, pKa plus pKb. It has to be 14 for whatever that system is. And so I'm going to write below this, if my eye will let me write this small. So pKa2, which is associated with pKb1, is just going to be 14 minus 4. So that's going to be 10. And similarly, the pKa1, the first acid dissociation step, is going to be 14 minus 9, which is going to be 5.0, and we'll use that one later. So we've got those written up here, which allows us to write pH is equal to 10, that's pKa2, plus log of those two species. At this point, though, we know they're equal to each other, so that becomes log 1, and so the pH is equal to 10 in this specific circumstance. And that's exactly what we see here, where we're at pK2. They're writing it as pK2, which I think is a little bit misleading because it's not clear whether they're talking about the acid or base form here, but anytime you're dealing with pH on the axis, then the pK associated with pH has to be the pKa. So they're talking about pKa2 there. So just as an aside, at this point, you would use this setup. You would use the Henderson-Hasselbalch with pKa2 and these two species, B and BH+, at any volume of acid added that's greater than 0 and less than 10. So this entire first buffer region, we call it, would require this expression. And the only thing that would change about this, here we knew that these two were equal to each other, so this collapsed the equation. If we didn't know that, if we said we added, say, like, I don't know, 6 milliliters, then we would have to use what we did before in the previous video, where we convert those 6 mils of acid to moles and then subtract that from the original formal concentration of B and add that to BH+. And so you would end up with an expression. You could either do that as an ice table, or you could do it directly in the Henderson-Hasselbalch equation, where you'd have 0.100, and convert that to moles, and then subtract the moles of H+ that were added, and then here you would add the moles of H+ that were added, and that would be your new Henderson-Hasselbalch expression. So it becomes a pretty versatile tool anywhere in that first buffering region. So also note, before I jump into the next point, that pH is equal to pKa at that first point where those two species were equal to each other, B and BH+, but also remember the volume there then is exactly halfway to equivalence. And that should make sense because you've converted exactly half of the original base into BH+. If you add another half equivalent, then you've converted all of it, which is the definition of the first equivalence point. And so on an assessed version of a problem like this, I may ask you just to really quickly compute all of these points, and they shouldn't take you that much time or effort because you're not having to do that much math. You're only having to remember sort of intuitively the volumes associated with these key points, right, where pK is equal to pH, that's halfway to equivalence, full way to equivalence, second equivalence, and then halfway between those points. Those are always going to be the same. And at least relative to each other, they'll always be the same. And so thinking through that will save you a lot of time if you're thinking more intuitively about it. All right, so now we're moving to point C. If you're looking at point C, it's where the arrow is. That's our first equivalence point. We already know the volume associated with that. We computed that. That was 10.00 mils, and we just did that using M1V1. As always, anytime you're at an equivalence point, you'll hear me echoing in your mind the question, that is, what do we have in solution at that point before or immediately before we allow the system to re-proceed to equilibrium? That's always the question you want to ask yourself at equivalence of any type of system, whether it's acid-base or redox, precipitation, whatever. And so at this point, in our first equivalence, what we've done is added exactly enough acid in this first step down here to protonate the base completely. And now we have, right before equivalence, everything in the form of BH+. But remember, and this is always the tricky part, in a diprotic system, BH plus can go two different directions, right? It could proceed and get protonated a second time to make BH2, 2 plus, so it could act as a base here, or it could act as an acid itself and go backward, and it could remove a proton or dissociate to give us the base again. So it can go either direction. And remember in the previous video we talked about this with relative pKa's here. If they're fairly far apart, which they are in this case 5 orders of magnitude, then the assumption or the approximation that we make at this point is that it's really not going to go very far in either direction, and the little bit that it does trickle in either direction is sort of going to cancel itself out. And so what we assume then is that BH plus here is equal to essentially the formal concentration of B, the original concentration of B that we started with. And at that point, there's two different ways to compute this. There's the explicit way, which comes from the systematic treatment, and I'll show you that here. Remember, the expression looks like this. So this comes from the systematic treatment. You can see this in my PDF handout, the use of this as well. Remember, F prime here is the adjusted formal concentration. So for the formal would be the concentration of this. The adjusted formal would be here simply because it took you some volume of acid to convert all of the original B to BH+. So you've got to adjust the original concentration to be a little bit more dilute because there's more solution, even though the moles of each are the same. They remain the same. So we could plug it in and compute this explicitly, but the approximation that we said was reasonably sound in this case is that if pKb1 and pKb, if those two pKs are reasonably spaced, meaning they're roughly 10 to the third or more spaced apart, in this case they're 10 to the fifth, then this systematic or explicit treatment here isn't really necessary, though you can use this, and I'll always give you this equation. So you'll always have this. This equation only pertains to the equivalence point between species in a diprotic system, where you have an amphiprotic system that can go either way. This is the only time this explicit treatment works. The other way that you can think about this, which is a geometric way that works especially when you have a reasonable magnitude distance between the two pKs, is we can say, well, at point B here, this point B was at pKa2, and this pK1 here is at pKa1, and exactly halfway between there, 1/2 pKa1 plus pKa2 has to be the pH where you're at equivalence. And so that approximation works really well here, and that's what we're going to use. All right, so I just plugged those values in. Be careful always, because if you're computing in pH, then you need to use the pKb's here. You could just as easily do this as POH and use the pKb's. That would still be fine, but you need, as long as you're computing a pH on the y-axis, you'll need to convert that back. So that'll be half times 10 plus 5, that gives us a value of 7.5, which is exactly what we see on the curve. If, just as an aside, I compute this value, this gives us 3.6 times 10 to the minus 8 molar as our proton concentration. Negative log of that gives us 7.50. And so I'm just showing you that the approximation in this case is completely sound, at least within the number of digits we're conserving. If we were trying to keep 5 or 6 digits, or even more than that, then that difference that the approximation insights would maybe manifest in error that would be within the number of digits we're conserving. So in this case, because we've got 5 orders of magnitude between the two, then that 5th digit, we're not keeping it here, and so it didn't manifest. These two are the same. But as I mentioned, solving things explicitly and not using approximations is always a safe bet. It just takes you more time and more effort and more resources. And so it's nice as you develop your intuition as a chemist that you're starting to think about, when can I shortcut and when can I not. It'll just make you a more thoughtful chemist in the long run anyway. All right, so point D here is our second buffer region. What do we know about the second buffer region? Well, it means that at the first equivalence, we converted all of the original B into BH plus, and now in the second buffer region, we're starting to run the second reaction here, where we're past the point of having just BH plus. Now we have a mixture of BH plus and BH2 2 plus. And so now we have a buffer of those two species. What does that mean? Well, it just means that we can use another Henderson-Hasselbalch, but in this case, we're instead of using pKa1 or pKa2, we're using pKa1. We're using that first pKa. And so we can draft this up as pH is equal to pKa1, 1 coming from the fact, again, that this is the first deprotonation step of BH2 plus log of the base version. The base here is the amphiprotic BH plus, and then the acid is the fully protonated version of the base. So this would be our system of calculation at exactly point D, where in that unique circumstance where our BH plus is equal to our BH 2 plus. So that collapses this equation where pH is equal to pKa1 being 5, and that's what we see here. So we could compute that. That's easy, but also know that, again, anywhere in the region from any volume added that's in excess of 10, so beyond the first equivalence, but just less than 20, the second equivalence, this is the expression that you'll use for that whole step. And so again, you can compute the moles added and subtract that. Or, as I mentioned, as another sort of shortcut, you can think about that as a fraction along the way. And so you know that it takes another 10 mils to fully destroy all of this and protonate this. And so you could, if you added, say, I don't know, 14 mils here, which would be here, you would be 4/10 of the way along the second equivalence point, which means you would have a total of 6/10 of your BH plus still remaining. And so if you're thinking about that relatively, you would have 6/10 over, in this case, our 4/10. And so it'd be 6/4, and you would solve that. That would give you pH. So that's a really handy trick when computing these things really quickly. This same sort of fractional approach would have worked in point B as well, thinking about the fraction of distance that you've come along that first equivalence, which is 10 mils. All right, so last point is point E here. This is our second equivalence point. And so again, the question I'll always ask you is, what do we have in solution at the moment that you are at the second equivalence? And so the second equivalence is the moment where you had originally BH plus in the solution, and you added exactly enough H plus to fully convert all of that to BH2 2 plus. And so everything now, at least pre-equilibrium, right when you've added the exact amount via your titration, everything is in the form of the fully protonated species. So that's equivalent to saying, at least in computing the pH, that's equivalent to saying, okay, you've got BH2 2 plus in your hand, and you toss that into water, and what's that going to do? Well, it's going to act like an acid, and it's going to protonate that stuff. So you're going to end up with some H3O plus the first deprotonated version of that pH. So this would be the expression that we need to consider in computing our pH, which makes sense for this because now you have an acid in solution, and you can see that the pH here is going to be acidic at that equivalence point. And so it's going to be the same setup where you have some formal concentration of BH2 plus, some amount X is going to go away, water is pure, and then some amount X is going to appear for both the H3O, in this case it's the same as H+, you know that, and the BH plus species. The thing that we have to be careful of here is that this F here we'll call prime, just because at this point the formal concentration 0.1 is no longer operative because we've added a bunch of liquid to the system, right? At this point we've added 20 mils, and so we've diluted our original 10 mils considerably because we added 20 on top of the original 10. So that F prime is the volume corrected formal concentration, just like we've talked about before. So we'll have to adjust that. At the same time, let's be clear what K we're using for this expression. So this is the fully protonated form in its first dissociation step. So that's got to be our first Ka. So this is going to be Ka1. So what we'll have is an expression that's Ka1 equal to x squared over f minus x, which we're used to having in this case. All right, so I'm going to compute the volume adjusted formal concentration just like I've done in previous videos. So I'm going to start with my original concentration of base. So this would have been B naught. So this is the same thing. And I started with 0.1 molar. I had the original volume. So this would have been V naught of the system. And then this would be V naught plus V E2, so the second equivalence volume that we added. And then this is just obviously a conversion factor from mils to liters so that we have moles per liter. So if I compute this, this gives me a value formal adjusted concentration of 0.0333 molar. So that allows me to punch this into my expression where I have, and actually I won't do that, but you have Ka1 simply by taking, so this would be 10 to the minus 5.00, and then this formal adjusted concentration is 0.0333, so solve for x. I solve this using the quadratic, and that gives me a value of 5.72 times 10 to the minus 4, and in this case this x is the proton concentration, so I can take negative log of that. That gives me a pH equal to 3.24, which is what we see on our curve here. All right, so I'm going to toss in one more point just to be clear here. It wasn't on the original curve in your textbook, but I just added it here as point F. And so point F is when you're beyond the second equivalence, and we know that at that point you've converted everything, well, at equivalence you've converted everything into BH2, and any drop of HCl you add beyond that, you're just adding strong acid excess to the system, which is this region of excess H+. So we got excess H+, so this becomes pretty straightforward. We just need to figure out what is the excess and then divide by the new volume of the system at whatever you've added. So let's consider that we've added 35.00 mils of HCl in this system. So technically this isn't where point F is, it would be like out here somewhere, so like 35, way out there. So remember, at this point we have everything in BH2 form. Really at 20 mils we had that, and there were 15 mils beyond that. So remember from a previous video, the assumption we're making here is that the this thing is going to dissociate. It's going to react with water to make BH plus some new protons. What we're assuming here is that the protons coming from HCl are going to be far more concentrated than the little bit of protons that come from this dissociation, simply because this is a small Ka. And so we're going to neglect any contribution here, and that's going to be reasonable, again, unless you're like a fraction of a mil past equivalence, in which case the proton concentration from HCl is comparable to the proton concentration from BH2, and then you'd have to treat it systematically, but I'm not going to make you do that. But thinking through that is important, that you understand that. So at this point we've got about 15 mils excess. Okay, so it's pretty easy to compute then. We just need the original concentration of the acid, so this would be our HCl naught, multiplied by how many mils excess we have, so that would just be the added volume minus the second equivalent, which puts us at 15. So we're at 35 minus 20 gives us 15 of excess. So in that case, That at this point in the computation, that would give us the moles of excess protons in solution, and then I'm going to divide that by our total volume to get us moles per liter, and then I'm going to have a final conversion step for moles per liter. If you do that, what does that give us? So that gives me a value of 0.02727. I'm not really being that careful with sig figs here, so don't hold me to the sig figs here. It's probably going to be, it actually might be, it might be 4. In which case the pH would be 1.5643 if I'm keeping all 4. Again, don't hold me to that, but this is generally how you'd approach any point that's in excess of the second equivalence.